In the early morning hours of November 11th, 2025, a soft but persistent anomaly crept into observatories around the world. From the dry plateaus of northern Chile, where the European Southern Observatory had just completed a night's worth of infrared calibration, to the silent automated nodes of Japan's Hida Observatory, to satellites orbiting high above the Pacific, every optical and radio telescope pointed toward one object, 3R Atlas. It had been stable for weeks, until it wasn't. At first the changes seemed minor, a minor drift in tracking data, an unresolved lock in the coordinate stream, nothing unusual in isolation. But within 7 minutes, data errors began synchronizing across systems. From La Palma, Arizona, Canberra, and even deep space satellites, the same pattern emerged. An unexplainable drop in signal resolution. Not a dimming, not a flare, not electromagnetic noise, just confusion. Instrumental focus began to blur, like curves flattened, edge definitions warped. Software routines trained on thousands of known celestial bodies failed to maintain target lock, and what replaced the data wasn't blackness or void, it was vagueness. A blank entry where certainty should be. Control rooms across 4 continents lit up with quiet alerts. Loss of object centering. Refraction mismatch. Target defocused. Even adaptive optics systems, engineered to self-correct in real time for atmospheric distortion, couldn't stabilize the view. Engineers rebooted modules, recalibrated sensors, double-checked local clocks. But none of it changed the outcome. Every tracking system had failed to resolve 3I Atlas's location, not because the object had moved, but because it had become momentarily unmeasurable. A presence without coordinates. It hadn't disappeared. It hadn't collapsed. It hadn't accelerated. It had simply slipped, out of sync, out of calibration, out of frame. And in those seconds that felt like static stretched across an entire discipline, physics blinked. The object reappeared soon after, returning to its expected location as if nothing had happened. But something had. It wasn't panic that followed. Not yet. It was a re-evaluation of constants, of reference frames, of assumptions that had gone unchallenged for decades. And then the silence came, not from the object, but from the observers. Because when every instrument blurs at the same time, and when that blur corrects itself without explanation, you're no longer studying a comet, you're interacting with a system. And on November 11th, for the first time since its discovery, 3I Atlas didn't just confuse scientists, it reminded them that measurement is not observation, and observation perhaps is not control. Before we begin, make sure to like this video and subscribe so you don't miss what comes next as the data unfolds, frame by frame, night after night. Tell us where you're watching from, and the time right now where you are. Because as of tonight, the story of 3I Atlas has changed again. And somewhere, millions of kilometers from Earth, that story may still be unfolding, silently, precisely, under the light of the same sun that powers every movement we're about to uncover. This is the 3I Atlas channel. Calm, focused, and based on real-time solar system data. If you want to be part of this mission, hit subscribe right now. Comment Atlas below to enter the giveaway for our exclusive 3I Atlas hoodie. Tell me where you're watching from and the exact time it is. You're now part of a global community tracking something the textbooks never prepared us for. At precisely 3 UTC on the morning of November 11th, 2025, an operator at the European Southern Observatory noticed a small red icon flashing on her telemetry screen. It was a minor alert, one that usually meant the target had drifted slightly out of frame because of routine mechanical lag. She cleared the notification and recentered the telescope. The system responded as it always did, motors whirring, mirrors tilting, sensors relocking. Then the warning reappeared. This time the telescope insisted the coordinates were invalid. She tried again. The target 3I Atlas should have been sitting squarely in the field of view. Its orbital parameters were precise to the 6th decimal. Yet the software refused to resolve it. The starfield behind it was sharp. The reference grid was flawless. Only the object itself had dissolved into numerical ambiguity. A presence without coordinates. Across the world, similar reports began to surface within minutes. At Mauna Kea, the adaptive optics array stalled mid-calibration. In Canberra, the automated scheduler logged a null return. At Cerro Tololo, the tracking lasers remained locked on their guide stars, but the reflection that should have bounced back from Atlas's surface simply never arrived. The initial assumption was hardware drift. Teams ran quick checks on gyroscopes, servos, and alignment motors. Everything was nominal. The sky itself had changed less than a fraction of an arc-second. Yet every instrument saw the same absence. Astronomers recalculated the object's right ascension and declination, cross-checking with last night's data. The difference was too small to suggest movement, less than 1/10,000th of a degree, but enough to render every tracking model useless. The coordinates, once stable, now slid unpredictably through each frame, like a reflection on unsteady water. At NASA's Goddard Space Flight Center, the control console displayed a stream of warnings. Guidance error 3S, reference mismatch. The algorithm tried to compensate by predicting where the object should drift next, but every iteration only increased the error margin. It was as though Atlas had stepped outside the geometry that defined position itself. By 0229 UTC, 5 observatories across 3 continents confirmed that their systems were experiencing simultaneous positional collapse. A request for intercomparison was sent through the Global Astronomical Network, and when the timestamps were aligned, a disquieting realization surfaced. All errors began at the same instant, synchronized to the microsecond. That ruled out local malfunction. It suggested a common cause in space. Engineers then looked for atmospheric interference, perhaps an upper layer temperature inversion or stray solar flare scattering light unevenly. But meteorological satellites showed clear skies. Solar wind indices were calm. Even cosmic ray flux remained below baseline. Nature was quiet. The problem was deeper than turbulence. It was structural. The next idea was time. Could a glitch in coordinated universal time have propagated through the network, skewing calculations? Atomic clock data from Boulder, Paris, and Tokyo disproved it. All clocks were in perfect phase. In fact, they had never been so precisely aligned. The only element misbehaving was the light coming from Atlas itself. When analysts overlaid data from optical, infrared, and radio bands, they discovered a faint but consistent phase offset. The photons arriving from 3i Atlas reached each observatory slightly ahead of their predicted schedule, by about 14 milliseconds on average. Not enough to break causality, but enough to imply that the object's apparent position had detached from its physical one. In practical terms, Atlas seemed to occupy multiple reference frames at once. At CERN's Data Integrity Lab, the phenomenon was given a provisional name, coordinate decoherence, a breakdown of positional certainty across synchronized systems. No one claimed to understand it, but the mathematics resembled quantum interference patterns scaled to astronomical distances. Something about the object's reflected light produced a self-cancelling oscillation, making its centroid impossible to define. By dawn, the crisis had reached the community's private channels. Observers compared screenshots, plots, and residuals. Every graph told the same story. Atlas hadn't moved, but the universe around it had lost its place to stand. And as the sun rose over the Atacama Desert, the astronomer who first saw the red warning light stared at the quiet sky through her recalibrated lens. The stars were where they belonged. Only one point refused to settle. She wrote a final note in the log: object visible, but unlocatable, coordinates present, then gone. That single sentence would mark the beginning of what researchers later called the first measurable fracture in the map of certainty itself, the moment when 3i Atlas taught science that position is not the same as presence. When the first wave of positional anomalies surrounding 3i Atlas hit observatories on November 11th, most scientists believed it would be a short-lived calibration issue, a transient misalignment, perhaps due to software drift or minor orbital noise. But by the time the data was cross-referenced with orbital mechanics logs, a strange contradiction emerged. Every long baseline array, including the NASA Jet Propulsion Laboratory and the European Space Operations Centre, confirmed the same thing. 3i Atlas had not changed its velocity. Its trajectory remained perfectly stable. There was no acceleration, no deceleration, no gravitational deviation. Every model, classical Newtonian, relativistic, or perturbation-based, held. And yet, the object no longer appeared in the same location across multiple viewpoints. The positions were off, not wildly, but unmistakably. The displacement was directional, angular and time-bound. The more closely you looked, the more the illusion broke down. It was motionless, but displaced. At the Mount Wilson Observatory, the team ran a centroid tracking routine that calculates the exact pixel-weighted centre of any moving body. What they found confused them. Over a 2-hour period, the centre of light shifted by 0.041 degrees, roughly the width of a golf ball seen from 20 miles away. Small, but not random. The object was standing still, but its image was not. One theory proposed that interplanetary plasma might be causing a mild lensing effect, a soft refraction from solar wind eddies, bending the light between Atlas and Earth. But satellite data from SOHO and stereo satellites showed no plasma density irregularities. The region of space Atlas occupied was magnetically smooth, with no turbulence strong enough to account for the observed drift. The real paradox was in the timing. The apparent displacement did not occur gradually. It flickered into existence and held, as if the object had quietly stepped into a different alignment, relative to every observer on Earth. There was no physical movement, yet visual confirmation betrayed a subtle shift. The parallax models refused to reconcile, as if Atlas had decided to exist slightly sideways. At the Kavli Institute for Astrophysics, a graduate team conducted a recursive comparison of Doppler shift signatures from the previous 5 days. Their results stunned everyone in the room. The emission line profiles, which had remained perfectly consistent since early November, now showed a mild redshift in the optical band, but not in the infrared. The object wasn't receding or approaching, yet its spectral lines had subtly skewed. Even stranger, the shift varied depending on the time of observation and the location of the observer. From Europe, Atlas appeared fractionally closer. From Asia, it appeared further away. From space-based sensors, it appeared unaffected. These weren't artifacts. The detectors were independently calibrated and cross-verified. The data was real. Engineers at the Deep Space Network posed a radical suggestion. What if 3i Atlas had changed its interaction with spacetime itself? Not through motion, but through orientation, some internal rearrangement that re-angled its emissions, projecting a slightly altered positional echo across Earth-based instruments. It sounded speculative, and yet all proposed natural causes failed. Solar radiation pressure couldn't account for it. Magnetic turbulence was ruled out. Gravitational lensing from nearby masses was not present. The only consistent feature of the displacement was its non-locality. Observers from around the world using different instruments detected the same pattern, a stable object whose position shifted without moving. At CERN, data analysts ran the signal through a phase coherence algorithm normally reserved for particle collision residue. The result was inconclusive, but the signal-to-noise ratio showed a strange frequency minimum at exactly 143 seconds after each recalibration. In quantum mechanics, this is called a null phase window, a condition where wave functions cancel one another just long enough to suppress a measurement. The implication? Atlas was not moving. It was interfering with the act of being measured. By mid-morning, scientists stopped asking if the object had moved. Instead, they began asking a more disturbing question. Can an object appear in a different location without moving at all? And if so, what does that say about the nature of observation? By noon on November 11th, the consensus was forming quietly across encrypted research threads and sealed briefing rooms. Displacement without motion is not a malfunction. It is an instruction. Something had changed, not in the object, but in the space between it and us. By 0216 UTC, the disruption caused by 3i Atlas had escalated from curiosity to operational breakdown. At observatories worldwide, automated observation systems began failing to complete basic commands. Not because of hardware errors, not because of bandwidth or environmental conditions, but because the object at the center of every tracking algorithm, 3i Atlas, had effectively stopped being trackable. This was not a theoretical problem. It was systemic. At the Solar and Heliospheric Observatory, SOHO, the imaging sequencer locked up mid-capture. The onboard software flagged an error, active target mask not found. The instrument, which had successfully tracked Atlas for over 3 weeks, could no longer isolate the object within its field of view. The failure wasn't in optics. It was in target identification, the core layer of the system responsible for knowing what it's looking at. Simultaneously, the James Webb Space Telescope, monitoring in the near-infrared, reported an internal fallback. Its thermal imaging suite entered safe mode after receiving conflicting calibration feedback from its mid-wave detectors. According to the logs, the onboard AI attempted to compensate for what it called adaptive thermal saturation. In plain terms, the light from Atlas was confusing the sensors. At first glance, this made no sense. The object had not become brighter. In fact, its luminosity remained constant within a 0.05% margin. But the internal systems disagreed. To them, something had shifted. Signal amplitude maps showed a perfect pattern, until BRUS 216. Then, scatter. The data went fuzzy, grainy, chaotic. At the Max Planck Institute, a team running a ground-based radio interferometer noticed something even stranger. The instruments were still operating. The antenna arrays were still collecting data. But every waveform came back empty, a flat line where a structured signal should have appeared. It was as if the signal was too precise to be detected. Not lost, but invisible to the method of observation itself. Meanwhile, at NASA's Ames Research Center, the situation escalated when their newly deployed adaptive optics platform failed to initialize. The software ran through its normal atmospheric correction sequences, realigning for distortion. But when it reached the final stage, target verification, it stalled. Then it shut itself down with one final log entry: no target curvature detected. Starfield mismatch. This meant something unprecedented had occurred. The instruments could see the background stars, sharp, defined, steady, but could not resolve the object in front of them. Atlas had effectively flattened in the detection schema. It did not curve, it did not deflect light, it did not scatter signal. At the European Space Agency, engineers dug into the diagnostic logs. What they found alarmed them. All the systems that had failed shared a common condition. They were running predictive error correction models based on previous frames. These models are designed to fill in missing data using pattern recognition. But with Atlas, they all produced nonsense. The feedback loops collapsed, creating what engineers described as recursive blind spots. In practical terms, the instruments couldn't just not see Atlas. They couldn't even process what not seeing it meant. At JAXA's Hayabusa Tracking Center, an internal memo used a term no one expected to read outside theoretical discussions: measurement failure due to target non-computability. The object had become mathematically undefined within systems built to predict motion, shape, and spectrum. These systems weren't damaged. They were just never designed to handle an observation that contradicted its own input. One theory suggested that 3i Atlas had subtly shifted its emission phase, altering the timing of photon arrival just enough to misalign high-resolution sensors. Another posited that its light field had become directionally anisotropic, visible only from certain quantum angular windows. But all these explanations shared one fatal flaw: they weren't testable. By 03-04 UTC, at least 19 observatories had experienced similar lockouts. Internal watchdog systems began disabling automatic calibration to prevent cascading system errors, and across dozens of research facilities, screens went black. Not because the object was gone, not because the sky had changed, but because the machines designed to measure it no longer knew how. By mid-morning on November 11th, as telescopes scrambled to recover their lock on 3i Atlas, one particular data stream caught the attention of a spectroscopy team at the Keck Observatory in Hawaii. The instrument in question, a high-resolution Echelle spectrograph, had been quietly running overnight, capturing frame after frame of the object's light across hundreds of finely resolved wavelength bins. When the team overlaid the morning's spectra onto the baseline from the night before, they expected the usual: a stable emission profile with some trace, ionized dust signatures and a few faint molecular bands typical of comet-like bodies. Instead, they found something that defied basic optical physics. The primary emission lines, those associated with Atlas's known spectral fingerprint, had not shifted. They had doubled. Side by side in the same dataset were two nearly identical spectral profiles, offset not by redshift or Doppler distortion, but by something subtler: phase separation. It was as if the object had begun projecting two versions of its own light signature simultaneously. Both were valid. Both passed calibration checks. but their separation was consistent, exactly 0.62 nanometers apart across every band. That distance fell between standard Fraunhofer lines, not corresponding to any known atomic or molecular transition. No known material or mechanism emitted in both channels like that, and certainly not with such clean repetition. At first, the team suspected a diffraction artifact, a common issue with overlapping Echelle orders, but control images from a nearby quasar taken moments before showed no doubling, nor did the comparison star. The effect was exclusive to Atlas. Within an hour, other observatories confirmed similar results. The Subaru telescope, also on Mauna Kea, using a different spectroscopic technique entirely, showed the same dual pattern. So did the Very Large Telescope, VLT, in Chile. Across the globe, scientists saw a single object emitting twin spectral profiles, each coherent, each slightly out of phase. The immediate question was simple: why? One hypothesis suggested optical birefringence, the splitting of light into two distinct beams due to interaction with an anisotropic medium. But birefringence requires transmission through structured material, like crystal lattices or polarizing layers. In this case, there was no intervening medium. The light had originated that way. A second theory drew from quantum coherence. If Atlas contained a field, magnetic, electric, or otherwise, capable of sustaining coherent photon states, it could, in theory, encode its emissions with internal phase information. That would explain the stable offset, but it wouldn't explain the energy symmetry. What troubled researchers most wasn't that the lines had split, it was that both sets carried the same intensity. Normally, when light divides through refraction, scattering or lensing, one path dominates. Energy is not shared equally. But here, both profiles were perfectly matched, down to less than 0.02% in photon count. That level of precision implied amplitude regulation, as if something was controlling the balance between the two signals. At the University of Cambridge, the light curves were fed into a phase decomposition algorithm designed for interferometric baselines. The output revealed a subtle beat frequency, a low-amplitude oscillation between the two channels, with a full cycle every 11.3 seconds. That beat was invisible in direct measurements, but clear in the interference pattern. In optical physics, such patterns only occur when two coherent sources interact. Lasers can produce it, so can entangled photon emitters. But no natural astronomical object had ever shown signs of such behavior. And then came the final discovery. The James Webb Space Telescope, still operating under reduced capacity, had recorded infrared spectra of the same region. When its data was overlaid with the split lines from Keck, analysts found a third profile. This one, hidden entirely in the near-infrared, matched the same structure as the first two, but delayed in time by 0.8 seconds. 3 sets, 3 signals. Each identical in form, each arriving through a different spectral window, and none of them showing any sign of energy loss. The implication was no longer subtle. Atlas wasn't just emitting, it was replicating, not as duplication in space, but as phase-separated outputs, precisely structured, tightly synchronized. The team at Keck drafted their internal report with one line underlined: "This is not splitting due to medium, it is splitting due to intention." And across the scientific community, a quiet discomfort began to take hold, because light isn't supposed to make decisions, not unless something behind it already has. By mid-morning on November 11th, one of the more curious anomalies began surfacing not from the optical or radio telescopes, but from a discipline often overlooked in deep space observation: photometric albedo analysis. Specifically, the way 3i Atlas reflected sunlight, or more precisely, how it appeared to reflect more than was physically possible. At the European Space Operations Centre, ESOC in Darmstadt, a team specializing in surface composition modeling reviewed standard albedo returns from Atlas's last known observation arc. They noticed something immediately strange. The object's bond albedo, a measure of total reflectivity across all wavelengths, had exceeded 1. This wasn't a rounding error. The system had calculated a reflectivity index of 1.14. In simple terms, it meant that Atlas was reflecting 114% of the light it received from the Sun. That is, by every known law of physics, impossible. Reflectivity, whether diffuse-like snow or specular-like polished metal, is bound by energy conservation. An object can scatter, absorb or reflect light but it cannot emit more reflected light than it receives unless it's generating energy of its own. But that's exactly what the instruments were suggesting. The team reran the data, assuming a calibration error. The Sun's incident light was modelled from 3 independent sources: the Solar Dynamics Observatory, the Solar Orbiter, and ESA's Proba 2 satellite. Each confirmed that solar flux in the region was stable. The incoming radiation was well within expected bounds. Yet, when compared to the measured outgoing light from 3i Atlas, the object appeared brighter than it should be, by a margin that couldn't be dismissed. At first, this triggered discussions about backscattering. In comet science, certain dust grains can reflect light preferentially back toward the Sun, enhancing perceived brightness at specific angles. But 3i Atlas wasn't near perihelion. It was not trailing a tail. There were no jets, no halo, no evidence of ejected material. In fact, its surface profile was among the cleanest ever recorded, a tightly bound luminosity with no surrounding dust cloud. Then came the angular reflectance analysis. Teams used bidirectional reflectance distribution functions, BRDF, to model how light was bouncing off the object's surface. The resulting plots were disorienting. Instead of a broad, diffuse reflection cone, the reflected light formed a tight collimated beam, directed with near laser precision back toward Earth-based detectors. In other words, the object wasn't just reflecting sunlight, it was shaping it. By noon, scientists at MIT's Lincoln Lab tried reconstructing the geometry using simplified surface models. No natural surface, not ice, not crystalline rock, not even polished obsidian, could create the reflectance pattern they were seeing. The light behaved as if it had passed through a structured photonic surface, a material engineered to interact with specific wavelengths. To test this theory, they adjusted their simulation to include a metamaterial surface, like those used in experimental optics on Earth. Synthetic lattices designed to bend or manipulate electromagnetic waves with microscopic precision. Only then did the model match, and yet metamaterials are not known to occur naturally. They require manufacture, or at least self-organized structuring beyond what cometary geology could explain. That's when researchers noticed something more unsettling. The angle of peak reflectivity was not aligned with the Sun, it was aligned with Earth. Across 6 observatories, light curves showed a consistent enhancement, not when the Sun was directly behind Atlas, but when Earth and Atlas were positioned at a 22-degree observational vector. The implication was subtle but profound. The object appeared to be maximizing reflectivity in our direction, not in response to light. At the University of Bologna, where polarimetric sensors were running alongside traditional imagers, a new discovery emerged. The reflected light was partially polarized, a trait that usually requires either extreme angle of incidence or engineered reflective surfaces, and this polarization was circular, not linear. Circular polarization is extremely rare in nature, and when it does occur, it typically results from interaction with biological materials, synthetic optics, or communication systems. In a private memo circulated among ESA research teams, one sentence stood out. The object does not reflect sunlight in a passive sense. It appears to redirect it with intent. To the public, the data would later be dismissed as overexposure or sensor bias. But among those still watching the light carefully, a conclusion was beginning to take shape. 3i Atlas was no longer behaving like an inert body. It was acting like a responsive surface, one capable of recognizing its observer and amplifying its return. And for a brief moment on November 11th, the planet that happened to be in the path of its brightest beam was ours. By early afternoon on November 11th, efforts to re-establish a stable lock on 3i Atlas had reached their most fundamental method, triangulation. If predictive software failed, if direct imaging wavered, if spectral models broke down, then astronomers would rely on the oldest principle in observational astronomy, geometry. 3 observatories, 3 perspectives, one set of intersecting lines through space to fix the object's position. It should have worked. At 13:06 UTC, a triangulation protocol was initiated between the W.M. Keck Observatory in Hawaii, the Roque de los Muchachos Observatory in La Palma, and the Cerro Tololo Inter-American Observatory in Chile. These facilities, separated by thousands of kilometers and aligned along different longitudes, had previously formed a reliable network for locating transient objects with extraordinary precision. The plan was simple. log a synchronized timestamp record Atlas's position, and feed the angular data into a shared coordinate solver. Each site performed flawlessly. Local sky conditions were clear. Their instrumentation returned exact timestamps with confirmed internal clock synchronizations, down to the microsecond. And yet, when their data was cross-processed, the results defied basic geometry. Each observatory's line-of-sight vector projected into space cleanly. But when extended outward, the three vectors never intersected. Keck's vector placed Atlas roughly 250,000 kilometers further along its orbital arc than expected. La Palma's model placed it closer, skewed several degrees off the ecliptic. Cerro-Tololo's projection was nearly orthogonal to both, suggesting the object had veered laterally. Normally, small discrepancies in triangulation could be attributed to error, mechanical offsets, atmospheric refraction, or subtle clock drift. But this was something else. Each measurement independently was valid, but together they could not describe a single position in three-dimensional space. The intersection point, where all three views should converge, simply didn't exist. Researchers referred to this phenomenon as a non-coincident solution. In astrophysics, this only happens when the object in question is not a point source, or when it changes position faster than light, neither of which were applicable here. Atlas's light curve was stable, its emission steady, its relative velocity suborbital. Nothing about it implied instability, and yet it refused to exist in one place. At the Harvard-Smithsonian Center for Astrophysics, a team attempted to resolve the discrepancy by introducing a new variable, time delay compensation. The idea was that perhaps the object's light was not arriving simultaneously to all locations due to some unexplained medium interference or propagation lag, but that effort only made things worse. Instead of converging, the triangulated paths diverged further, as though the object had fractured into multiple phantom positions, each one consistent with one viewpoint and incompatible with the rest. That's when the term probability shell began circulating. It described what the data suggested, that 3i Atlas was not a point in space, but a volume of probabilities distributed around a core that no one could directly observe. In quantum physics, this is normal. Electrons behave this way around atomic nuclei, but this wasn't quantum, it was planetary scale. At the European Space Agency, a simulated re-render of the triangulation attempt was performed using high-fidelity orbital physics engines. They visualized the three position lines as they extended into the heliocentric frame. What emerged was astonishing. Instead of lines crossing, they formed a triangle, a perfect geometric boundary surrounding an empty point in space. That center, the missing intersection, was nowhere to be found. The ESA simulation team referred to the space inside that triangle as the blind core. To confirm the results, a fourth observatory was added, Siding Spring in Australia. Their data only deepened the paradox. Instead of helping narrow the solution, the new vector collapsed the triangle into a shifting quadrilateral, its shape morphing in real time depending on the time of data entry. One analyst commented privately, "It's not that we can't see it, it's that we can't agree on what it is." By evening, attempts at triangulation were halted, not because the object had vanished, but because the process itself had become meaningless. The conclusion, however unspoken, was unavoidable. You cannot triangulate an object that refuses to exist in only one frame of reference. And on that day, 3i Atlas broke one of the most sacred tools of astronomy, not by hiding, but by being too real, from too many directions at once. As traditional triangulation, methods collapsed under the weight of contradiction. A new line of inquiry opened quietly inside a secure modelling room at the European Space Operations Centre, ESOC. If 3i Atlas could no longer be fixed in place using standard observational geometry, perhaps the solution lay not in the object, but in the space surrounding it. By 14 to a UTC on November 11th, orbital engineers at ESOC began reprocessing Atlas's trajectory using dynamic solar system simulations. What they found shocked even the most seasoned analysts. 3i Atlas wasn't passing randomly through heliocentric space. It had entered, with uncanny precision, a dynamically unstable orbital saddle, a region of space where multiple gravitational influences cancel one another out. Specifically, it had positioned itself within a transient null zone, a floating corridor between Earth's gravity solar radiation pressure, and subtle magnetic drifts from the heliospheric current sheet. In orbital mechanics, such null zones are notoriously rare and difficult to map. They exist not as fixed locations, but as moving pockets, balancing points formed by the constantly shifting interaction of planetary masses, solar wind, and time-based gravitational delay. Under ordinary conditions, natural objects avoid them. Null zones are unstable by nature. Even a slight force imbalance, a solar gust, a micrometeorite hit or internal pressure shift, can eject an object from such a space, but Atlas wasn't ejected. It had centered itself inside the zone with millimeter-level precision. The region it occupied was mathematically known as an unbounded saddle point, a topological anomaly in the gravitational potential field. These points are so fragile that even the movement of the Moon can deform them. Yet Atlas remained perfectly suspended. At first, the team assumed coincidence. Perhaps the object had drifted into the null zone unintentionally, an artifact of orbital drift and solar wind interference. But the longer they modelled it, the less likely that seemed. Null zones move, and 3i Atlas was moving with it. The simulation showed that over a 36-hour period, the null pocket had drifted by nearly 2,800 kilometres, nudged by Earth's rotation, Jupiter's long-range gravitational influence, and subtle density waves from the solar wind. And in every single timestamp, Atlas maintained its relative position within the centre of the null. That meant only one thing. The object wasn't occupying the null zone, it was tracking it. Engineers cross-checked the position history with past cometry data, asteroid flybys, and artificial satellite paths. Not once had a natural object ever demonstrated this kind of dynamic alignment with a non-fixed, unstable orbital point. Even spacecraft designed with precision station-keeping thrusters struggle to maintain such positional coherence without constant correction. But 3i Atlas required no course correction. It simply followed the path, as if it had known where to be. To better understand the surrounding geometry, ESA's modelling team visualised the local spacetime curvature as a mesh of gradients, plotting the gravitational potential field in 3 dimensions. The result was a visual anomaly, a toroidal depression, a ring-shaped zone of equilibrium with Atlas precisely at its lowest point. It was as if the object had curved space into place around itself, not the other way around. This visual didn't match any natural body's behaviour. The torus resembled active gravitational modelling, the kind proposed in advanced theoretical propulsion systems, systems that shape local spacetime to maintain drag-free motion. That afternoon, a physicist from the University of Oslo quietly suggested an even more radical model. She proposed that Atlas was behaving not like a passive mass, but as a sympathetic oscillator, an object tuning itself to the ambient frequencies of nearby fields. In this model, the object didn't stabilize within the null zone. It generated one, moment by moment, by synchronizing with the natural harmonics of space. The model fit. But it made no sense, unless one accepted a disturbing premise that the object understood the environment better than the environment understood itself. One ESOC analyst wrote in their log, "This object is not riding the wave, it is steering into silence." By the end of November 11th, the null zone remained undisturbed. Every new simulation returned the same result. Atlas was not where it needed to be gravitationally. It was where it shouldn't have been able to stay. And somehow, it was most stable in the one place the universe refused to hold anything still. In classical astronomy, parallax is a foundational principle, a simple geometric truth that underpins everything from star charts to deep space navigation. When you observe a distant object from 2 separate vantage points, its position appears to shift slightly against the background. This shift, called parallax, is predictable, measurable, and proportional to distance. It's how astronomers calculate the position of planets, the distance to nearby stars, and even how the brain perceives depth. But on the morning of November 11th, 2025, 3i Atlas violated that truth. At 15:20 UTC, during a routine position verification cycle, the team at the National Astronomical Observatory of Japan, NAOJ, noticed something wrong with their angular offset measurements. They were cross-checking simultaneous observations with the Arecibo Successor Array in Puerto Rico and the South African Astronomical Observatory. The idea was simple: compare the position of Atlas against known background stars from 3 separate locations. calculate its parallax shift, and confirm its current distance. Except this time, the shift was inverted. Instead of appearing to move against the background as the Earth rotated, which would be expected from any nearby object, Atlas appeared to move with it. The object's apparent position shifted in the wrong direction. The initial report called it a parallax inversion, a term that technically didn't exist in professional astronomy. But the numbers didn't lie. From Tokyo, Atlas appeared to nudge westward. From South Africa, the same. From Puerto Rico, again, the same bias. Each system's software flagged the error as an observational artifact, suggesting a local calibration fault. But when they triple-checked their starfield geometry and compared inter-observatory timestamps, it became clear. All instruments were functioning properly. The problem was not the observers, it was the object. It was as if 3i Atlas had changed reference frames mid-observation, anchoring itself not in a fixed location, but in an angular position that mirrored the expected result. This inversion produced what astrophysicists at Caltech later called a negative parallax vector, a condition where the apparent motion of an object implies it is located behind the observer, not in front of it. That, of course, is impossible. Parallax is a spatial effect. It arises from geometry, not perception. The Earth moves, the object stays, the angles change. It's a fixed relationship. For Atlas to produce an inverted result, it would have to behave like a lens, bending or reprojecting its own image against its true motion. To investigate further, data scientists at the University of Cambridge attempted to simulate the optical environment around 3i Atlas using ray tracing models. They factored in solar light, heliospheric density gradients, and background star distribution. Their model only returned an inverted parallax result when they introduced one unlikely variable, a localized distortion field, roughly 180 meters across, capable of dynamically altering light paths. The model fit the data, but it came with a caveat. The field would need to adjust its geometry in real time, specifically in relation to each observer's location on Earth. That meant the distortion wasn't passive, it was responsive. To verify, researchers ran a series of synchronized observations using pairs of observatories at antipodal points, exact opposites on the planet. If the inversion was an atmospheric fluke, the results would cancel, but they didn't. Instead, both locations recorded matching negative parallax vectors, separated by time and geography, yet consistent in direction and magnitude. By late afternoon, a hypothesis emerged. 3i Atlas wasn't emitting a simple image. It was projecting a position, not fixed in space, but calculated relative to the viewer. That interpretation brought the conversation dangerously close to one long dismissed in astronomy: observer dependence. The idea that an object could react to being observed is common in quantum mechanics, but unheard of at planetary scale. And yet Atlas was now exhibiting behavior that could not be explained by distance, speed, or angle. It was defying spatial logic, not by vanishing, but by reversing its geometry when watched. An internal memo at NAOJ summarized it with unsettling simplicity. Either the light is bending, or we are. In the hours that followed, parallax measurements were suspended. There was no longer confidence in what was being seen. The error wasn't mathematical, it was perceptual. And as night fell across the Earth, 3i Atlas continued drifting, not through space, but through the trust placed in our ability to measure reality itself. In astrophysics, light curves are the heartbeat of observation. They're the cleanest, most empirical way to understand how an object behaves over time. Every comet, asteroid, and interstellar body has one, a signature rise and fall of brightness that reveals shape, spin, reflectivity, and even surface composition. These curves are used to model behavior, to forecast paths, and to detect hidden structure. They don't lie. But on November 11th, the light curve of 3i Atlas began lying, or at least behaving in a way that no one could interpret. At 1645 UTC, analysts at the Lowell Observatory were comparing two observational datasets, one from the previous night and one taken just an hour earlier. Both light curves were from the same telescope, using the same filters and the same software pipeline. At first glance, the curves looked identical, matching peaks, identical troughs, clean periodicity. But when the two graphs were overlaid, a strange detail emerged. The waveforms were not aligned. One was delayed, slightly but consistently by exactly 2.31 seconds. Initially, this was dismissed as a timing sync issue, maybe a local timestamp error or clock drift, but when they checked, the system logs showed full synchronization with the International Atomic Time Standard. No error, no drift. So they went deeper. They pulled additional light curves from the Apache Point Observatory, the Pan-STARRS network in Hawaii, and the McDonald Observatory in Texas. The goal was to build a global sample and isolate the offset. What they found was unnerving. Each light curve matched the waveform of the others, in amplitude, frequency, and profile, but every site recorded it at a slightly different phase. The delay wasn't random. It followed a precise geospatial pattern. The team plotted these time shifts against Earth's surface rotation and observer longitude. The result formed a sinusoidal distribution, the kind you'd expect from a signal rotating independently of the Earth, yet reacting to each viewer's position. In effect, 3i Atlas wasn't emitting one consistent light curve. It was emitting a rotating signal, synchronized to something outside of Earth's frame of reference. The implication was staggering. In classical emission, a rotating body like a comet reflects sunlight asymmetrically as it spins, creating a predictable flicker. But the reflected light remains consistent across observers. Only the timing of observation shifts. In this case, however, the object's light pattern itself was shifting, not just the observation. To test the idea further, the team at MIT developed a model based on a phase-lagging rotating emitter. This is a theoretical structure, one that actively rotates its emission profile while simultaneously adjusting the phase of output light based on observer vector. It's a concept found in directional antenna theory, not in natural astronomy. Their model fit the data perfectly. But here's the problem. For a body to do this, it must possess two capabilities. It must be able to sense the direction from which it's being observed. It must be able to adjust its signal output in real time per observer. There is no known natural object, cometary, asteroid or otherwise, that behaves this way. The only analogues come from human-made technologies, phased array radars, variable lens emitters, or adaptive LiDAR systems, all of which require active control systems, power and intent. The phase difference between the observers wasn't just a curiosity, it was predictive. Once mapped, the team could forecast the exact moment each observatory would receive its slice of the light curve, to within hundredths of a second. At that point, it was no longer about light delay, it was about information encoding. One senior analyst at Pan-STARRS wrote in the internal notes, "We're not looking at a reflection pattern, we're looking at a rotating broadcast, one whose phase is local to each observer. That's not just rare, that's deliberate." What began as a brightness measurement had turned into a global puzzle, one that hinted at something far more structured, far more intelligent, and far more advanced than any known object. By sunset, observatories were no longer just tracking brightness, they were tracking synchronization, and none of them could say for certain what they were syncing to. At first, the reports seemed like technical glitches. Image analysts from observatories around the world began noting strange inconsistencies in their stacked frames of 3i Atlas. Inconsistencies that couldn't be explained by atmosphere, lensing, or motion blur. In images captured just after 1730 UTC on November 11th, the object was sharp in a single exposure, but when frames were combined, a standard practice to reduce noise and improve signal, the result was strangely degraded. Instead of a sharper image, the stacked composite appeared softer, blurred, but not in a uniform way. In astrophotography, this is unheard of. More data always leads to more clarity. Stacking multiple exposures typically amplifies resolution and reveals fine structure, comet tails, rotational ridges, even coma asymmetry. But with 3i Atlas, the opposite was happening. More data led to less definition. This anomaly was first detected at the Isaac Newton group of telescopes on La Palma. An overnight team, reviewing high-zoom composites of Atlas's core, noticed that the object's edges did not sharpen with increased exposure time. In fact, when stacked beyond a 3-frame sequence, the object's outer structure began to dissolve into a radial smear, not due to light saturation, but as if its perimeter was being erased. At first, they suspected tracking jitter or mechanical slippage in the mount, but star fields remained perfectly sharp. Only the object degraded. When the same test was repeated using entirely different mountings, across different facilities, including the Gemini North Telescope in Hawaii and the Vista Survey Telescope in Chile, the same effect was recorded, but only for 3i Atlas. This prompted a new wave of investigation using point spread function (PSF) analysis, a technique designed to mathematically model how a telescope blurs light. Normally, PSFs are symmetrical. Light from a star or point source expands in predictable rings or spikes. But with Atlas, the PSF varied frame by frame, sometimes even across the same exposure. What the data revealed was deeply counterintuitive. The object's blur wasn't random, it was adaptive. A full sensor breakdown at the Institute for Astronomy in Edinburgh discovered that Atlas's image degraded in direct response to the type of data being gathered. When the exposure time was short, under 5 seconds, the blur was minimal. But when the exposure passed 20 seconds, the object's definition began to bleed outward, as if it were responding to extended observation by diffusing its outline. Even more strangely, the rate of blur matched the resolution threshold of each telescope. High-resolution systems with fine pixel scaling suffered more rapid degradation than low-res wide-field systems. The higher the clarity potential, the faster Atlas seemed to dissolve. This was not natural motion, it was not tracking error, it was not atmosphere. It was as if the object was selectively defocusing itself, depending on how intently it was being watched. An experimental trial was launched by the Max Planck Institute for Astronomy, using randomized exposure bursts to try and trick the object. Their automated scripts alternated between sharp bursts and blank frames to observe whether the blur could be disrupted, and it could, for a moment. The first few frames were crystal clear, but as the sequence continued, the blur reasserted itself, gradually pulling the object's outer shape into a fuzzy ring. They called it shadow softening. One physicist likened it to active camouflage, but not in the visual sense, rather in the informational one. The more precisely scientists tried to define Atlas's boundaries, the more the object refused to let them. And then came the final twist. When the same image stacks were processed using AI-powered upscaling tools, the models failed, not due to lack of resolution, but because they couldn't find consistent structure. Atlas wasn't just visually blurry, it was structurally fluid, like an object with no single edge, no definitive surface, no fixed boundary. One postdoc at Edinburgh summarised the finding in a single sentence that was quietly passed around the Slack channels of multiple observatories that evening. The harder you look, the less there is. On that November evening, telescopes across the Earth were focused on a single point in space. But the thing they were staring at, the comet, the object, the anomaly, was staring back with a subtle, calculated blur. And for the first time in astronomical history, resolution itself became a trap, one that 3i Atlas had already outmaneuvered. Precisely 1810 UTC on November 11th, 2025, the signal processing team at the Goldstone Deep Space Communications Complex noticed something that initially seemed impossible. While reviewing radar telemetry logs from a passive scan of 3i Atlas, they identified a faint anomaly buried within the return channel, a strange low-intensity pulse that didn't match the original transmitted waveform. The signal wasn't stronger than noise, but it was reversed. Not in polarity, not in spectrum, but in time. In radar systems, echoes are fundamental. A radar beam is sent, it bounces off a target and it returns, delayed by the distance to and from the object. But this time, Goldstone's system logged a return before the outbound pulse reached the object, a negative timestamp. The anomaly showed a response with a signature that matched the transmitted ping, down to the microstructure, but arriving 10⁸ seconds too early, as if 3i Atlas had known the pulse was coming and returned it before it was sent. This wasn't a mechanical glitch. Goldstone's radar systems are synchronized with deep space atomic clocks, accurate to billionths of a second. The facility ran self-diagnostics, checked their local timing chains, verified GPS sync, and still found no fault. So they did what scientists are trained to do when the data defies theory. They repeated the test. Goldstone reissued a tightly focused pulse toward Atlas, this time with a chaotic waveform designed to be unpredictable. The goal was to avoid pattern matching that might create artifacts, but once again, the echo came back just under half a second before it should have. It matched the shape of the transmission, even though the transmission hadn't occurred yet. The return pulse was faint, near the edge of noise, but consistent across multiple iterations. When the waveforms were inverted in time and overlaid, they aligned perfectly. This wasn't an echo, it was a time-reversed mirror. At the Lunar Laser Ranging Experiment in New Mexico, similar tests using light pulses instead of radar returned equally strange results. Instead of a single sharp echo, their detectors recorded dual peaks. One at the expected time and one before the laser had completed its cycle. The early pulse was always weaker, always inverted, and always exactly proportional to the outgoing waveform. It was as if 3i Atlas was sending signals backward, not through space, but through time. To rule out software artifacts, both radar and laser facilities switched to analog recording systems and external synchronization references. Nothing changed. The pre-echo remained. Researchers at Max Planck Institute for Radio Astronomy proposed a radical theory. What if 3i Atlas was surrounded by a phase-conjugating surface, a material or field that could reverse the direction of time within a localized wave structure? This is a real concept in advanced optics and signal engineering, used in nonlinear crystals to create mirror beams that backtrack their original paths. In lab conditions, it works, but it requires immense precision, precise material properties, exact beam alignments, and artificial media. There's no known natural phenomenon capable of generating such an effect at macroscopic planetary scale, unless, that is, 3i Atlas wasn't behaving like a solid object, but like a signal handler. If the object was less like a rock and more like an interference node, then the strange radar and laser effects made a different kind of sense. It was behaving like a time domain filter, one capable of not just bouncing waves, but re-emitting them as though time was simply another axis to bend. A theoretical paper, circulated internally but never published, labelled the phenomenon a causal inversion artifact. Its conclusion: this object does not merely reflect, it anticipates. In a private call between NASA and ESA teams later that night, one senior physicist asked the question everyone had been silently avoiding. If it can return a signal before we send it, what else might it already know? Because if 3i Atlas could see into our instruments before they acted, if it could read our approach before we made it, then it wasn't just ahead of us in space, it was ahead of us in time. By the evening of November 11th, the largest observatories and data centers around the world were no longer relying on raw optics to study 3i Atlas. Instead, they turned to their most powerful resource: predictive algorithms, the kind trained on decades of deep space trajectories, object behavior patterns, and dynamic orbital modeling. These systems, often built using neural networks, Kalman filters, or Bayesian estimators, had been used to predict asteroid collisions, comet outbursts, and even spacecraft anomalies years in advance. They were, in effect, the probability engines of modern astronomy, and one by one they began to break. At 1915 UTC, the European Southern Observatory ran a standard forecast sweep using their in-house tracking model, named Observer, to project the next 12 hours of Atlas's position and orientation. The result looked normal at first, a standard arc consistent with its current velocity. But when compared against live data just 15 minutes later, the real-time location was already off by over 4,600 kilometers. This was far beyond tolerable error. Even highly volatile comets don't deviate this dramatically in such a short time frame, unless acted upon by a massive force. And there had been no recorded gravitational events, flares, or debris impacts. Assuming an input error, they restarted the model using adjusted parameters. Again, the trajectory failed, in a completely different direction. A third attempt, using raw observational input with no human bias, resulted in a looping path that returned to its origin, a closed prediction curve implying retrograde motion, which had no physical basis. Meanwhile, the SETI Institute, using a deep learning neural net called Archive, experienced something more peculiar. When fed real-time data on Atlas's light curve and radar signature, Archive began generating a probabilistic heat map of possible behaviors. Instead of narrowing toward a high-confidence outcome, the algorithm expanded the uncertainty field with every new input. The more data it received, the less sure it became. After 10 minutes of continuous input, the model produced a 3D probability cloud so wide that it spanned 1/3 of Earth's orbital diameter, implying the object could be anywhere within a massive region of space, despite it being visibly tracked by over 40 active systems. This led to a term that quickly spread through internal networks: prediction inversion. It described the phenomenon of an AI model becoming less accurate the more data it absorbed, a reversal of the foundational assumption behind all machine learning. At NASA's Jet Propulsion Laboratory, a supervised model was deployed to run Monte Carlo simulations, a statistical method that simulates thousands of future outcomes based on small variations in current input. The goal was to identify any stable trend, no matter how faint. But instead of forming clusters, the simulations diverged exponentially. In under 40 iterations, every output became either chaotic, self-collapsing, or temporally recursive, outcomes where the object's position was dependent on future positions that hadn't occurred yet. One result showed Atlas arriving at a future point before having passed through the intermediate coordinates. Another suggested a return to a position it had already exited, but with a different light signature. JPL paused all simulations shortly after. There was no bug. The algorithms were functioning exactly as designed. It was the input, Atlas itself, that was violating the rules of prediction. A physicist from the University of Oxford, reviewing the failures, proposed that Atlas may be operating outside deterministic physics entirely. In his internal summary, he wrote, "Every time we model its future, we overwrite the past. The object's behavior isn't irrational, it's non-causal." That same night, several facilities began disabling live prediction overlays from their telescope interfaces. They returned to manual tracking, not out of preference but necessity. The digital assistants built to guide them had become liabilities, and so, for the first time in decades, space agencies reverted to visual confirmation, trusting only what they could directly observe, moment by moment, frame by frame. Because when even the best algorithms lose the ability to guess, it means something new has entered the system. Not just an object that defies forecasting, but one that refuses to be known ahead of time. By the late hours of November 11th, 2025, as predictive algorithms failed and geometric models collapsed, a new anomaly began to take shape, not in space, but in spectrum. Multiple observatories, now forced to return to raw signal analysis, began to notice something deeply troubling about the light signature of 3i Atlas. It had too many wavelengths. Every object in space reflects, emits, or absorbs light in specific ways. Stars shine across wide spectra, while comets and asteroids typically reflect narrow bands of sunlight based on their surface composition. Dust, ice, rock, or volatile gases. The reflectivity curves are as distinctive as fingerprints. But when the Very Large Telescope in Chile scanned 3i Atlas using high-resolution spectroscopy that night, they detected a full spectrum return, not just the normal visible range, but also deep infrared, near ultraviolet, and even narrow-band microwave frequencies, all occurring simultaneously. This wasn't just rare, it was physically inconsistent. Natural bodies can emit thermal radiation and reflect solar light, but not at perfect intensities across such a broad span. And certainly not with the same wavelength architecture observed from 3 different facilities, each using unique filter arrays. When compared side by side, the spectral readouts from Chile, Spain, and Australia all showed one exact overlap, a recurring triplet structure, 3 dominant peaks at precisely aligned intervals spaced in a ratio of 1.24. That ratio does not occur naturally in cometary reflectance, nor in blackbody emissions. More disturbingly, the same triplet was observed in bands that should not overlap at all, such as deep infrared and X-ray. The frequencies were cloned, not translated. That is, the pattern wasn't shifting from band to band. It was repeating itself identically across them. It was as if 3i Atlas was duplicating its wavelength identity, over and over again, across the electromagnetic spectrum. This phenomenon was quickly dubbed wavelength cloning. Engineers at the National Radio Astronomy Observatory tried to simulate the signature using controlled emissions from phased antenna arrays. While they were able to reproduce overlapping frequency peaks using coherent pulse modulation, they required precisely timed phase alignment and active emission circuits, tools reserved for synthetic radio sources and military-grade beacons. There is no known natural mechanism for such cross-spectrum phase, replication, not in dust clouds, not in comet tails, not in ice shell reflection. One leading theory suggested that 3I Atlas may be surrounded by a metamaterial shell, a structure capable of bending, absorbing, and re-emitting light at desired intervals. Such materials exist in lab prototypes, often used in stealth or cloaking research, but those applications operate at narrow bandwidths, not across half the electromagnetic spectrum. To test the theory further, scientists at the Tata Institute of Fundamental Research attempted to filter out each known band individually, hoping the object's signal would degrade, but it didn't. Instead, it simply recreated the triplet in the remaining bands, even in thermal infrared, where no active emission should have occurred. The implication: the object was not just broadcasting light, it was encoding structure into frequency. It wasn't a visual signal, it was data. When the triplet was run through a software designed to search for non-random sequences, typically used in SETI to scan for artificial intelligence patterns, the waveform was flagged as structured. Not just regular, but self-similar across scales. The analysis returned a fractal probability score above 0.91, far beyond anything expected from noise or reflection. One researcher at the VLT put it simply, "It's as if the light is aware of itself, not just existing, but reintroducing itself again and again across every band we try to watch it in." By midnight, wavelength cloning had been confirmed by 7 observatories. The object was no longer hiding in space, it was hiding in frequency, becoming visible and yet unreadable, no matter how it was observed. And in doing so, 3's Atlas had done something no natural object had ever done before. It had weaponized visibility, turning the very act of detection into a recursive puzzle. At exactly 2042 UTC on November 11, 2025, while attempting to resolve the increasingly scrambled signal geometry of 3I Atlas, a team at the Swedish Institute of Space Physics made an observation that redefined the problem. They had been tracking minor fluctuations in magnetometer readings, background field distortions typically associated with solar-wind interactions or geomagnetic activity. But these readings didn't match any known solar patterns. There were no flares, no coronal mass ejections, no shifts in Earth's magnetosphere. Instead, the disturbances were localized, directional, and traced directly back to a point source, 3I Atlas. As they analyzed the vector field strength, a strange geometry emerged. The object wasn't emitting a uniform magnetic field. It wasn't radiating in a sphere, like a planet. It was bending ambient magnetic flux around itself, creating a lens-like distortion, precisely analogous to the way gravitational lenses bend light. Except this wasn't gravity, it was magnetism. This was immediately picked up by independent facilities across Canada, Norway and Australia. Their ground-based magnetometers showed parallel results. Sudden micro-deflections in the horizontal and vertical components of Earth's magnetic field, always shifting in alignment with Atlas's real-time position, as if the object was dragging the field lines along a mobile axis. These anomalies did not follow Earth's rotational motion, nor did they sync with solar wind direction. Instead, they formed converging patterns, all pointing toward a common focal line, an invisible axis of magnetism that passed through the object and extended miles beyond it in both directions. It was acting like a magnetic lens, concentrating, warping, and redirecting field lines, just as a glass lens bends light. The implications were immediate and startling. Lensing in physics is typically a function of mass or refractive index. Gravitational lensing requires enormous celestial bodies. Magnetic lensing, on the other hand, has only been observed in highly controlled plasma environments, such as magnetic bottles in fusion reactors, where intense coils force charged particles into curved paths. But 3I Atlas was doing it in open space, with no visible power source, no containment field, and no discharge. The lens effect was clean, quiet, smooth. To verify the phenomenon, the Swedish team ran multi-axis vector simulations, mapping the flux curvature around the object's known location. The model held, not only confirming the lensing behavior, but also identifying a secondary focal point roughly 19,000 kilometers behind the object's path. This shadow point, when mapped against background starlight, revealed subtle distortions. Background stars appeared microscopically displaced in a direction consistent with field warping. In short, 3I Atlas was magnetically refracting space. Further observations from the Advanced Composition Explorer ACES satellite confirmed a significant drop in proton flux directly downstream of the object. Charged particles that should have been striking the satellite were being deflected, as though passing through a field corridor like water diverted by an invisible barrier. This wasn't magnetic shielding as seen in spacecraft or planetary magnetospheres. This was magnetic redirection, an active manipulation of local field vectors. And then came the twist. During a parallel observation run, a team from Kyoto University attempted to image the object using polarized light. When viewed through a circular polarization filter, which normally helps detect aligned fields, the image of Atlas not only became clearer, it duplicated. Two ghost-like versions of the object appeared, slightly offset from one another, blinking in and out with filter rotation. This wasn't reflection or diffraction. It was field mirroring, light following bent magnetic paths to form virtual images, akin to the way mirages form in heated air. At that moment, the magnetic lensing was no longer just theoretical, it was visible. A memo circulated among observatory directors worldwide that night read, "We are no longer watching a comet, we are watching a field effect, one capable of realigning magnetism, redirecting plasma, and altering the very geometry of our perception. And if 3i Atlas could do that to magnetic fields, one of the fundamental forces that govern particle behavior and energy flow, then it was not simply reacting to space, it was reconstructing it." By the final hours of November 11, 2025, scientists weren't just looking at 3i Atlas, they were dissecting it, not physically but mathematically. And what they began to uncover wasn't a structure of mass and motion, but one of self-repetition. What looked like a comet from afar began to reveal signs of recursive geometry, patterns within patterns, repeating across scale and perspective as though the object had been built by equations rather than nature. The first hint came from the Gemini Observatory in Hawaii, which had initiated an advanced Fourier transform analysis on high-resolution reflectance images. This technique, typically used to identify repeating structures in crystalline materials or electromagnetic waves, was applied to surface scatter from 3i Atlas's core region. The result was astonishing. The object's surface reflected light in a non-random, non-chaotic pattern. Instead, the reflections produced nested periodicities, subtle, repeating ridges and troughs that scaled down at a consistent logarithmic interval. This meant the pattern on its surface wasn't just similar in some places, it was fractal, a recursive form, mathematically scalable, and self-similar across multiple resolutions. To verify this, an independent team at the Université de Montréal ran a wavelet transform, isolating detail at different frequencies within the object's light signature. This revealed something even more puzzling. At each zoom level, the shape of the emission echoed the structure seen at the previous one, almost like zooming into a Mandelbrot set. No matter how deep they scanned, the same patterns kept reappearing. This wasn't natural erosion, not thermal cracking, not gas jets. It was deliberate nesting. The phenomenon was dubbed recursive geometry detection, and it quickly became one of the most hotly debated findings of the night. The term referred to the object's apparent use of scale invariance, a property found in some natural phenomena like snowflakes or coastlines, but never to this degree of precision or frequency. With Atlas, the scale invariance was not an artifact of randomness. It was too clean, too exact. The object seemed to contain geometries that referenced themselves, creating a feedback loop of form. Researchers attempted to render a 3D model using fractal equations. They didn't have to go far. When they applied a basic inverse square fractal field to the object's outer shell, the resulting model matched the radar, contour data from earlier in the day. In short, 3i Atlas could be partially described by recursive equations, the kind used in artificial compression, computer-generated graphics, or even signal packaging. The implications were wild. If the object's outer structure could be compressed into fractal logic, then it meant two things. Its appearance was not random. Its appearance might be optimized for transmission. A comet doesn't encode itself, but this thing did. Further spectral decomposition of its surface emission by the Institute for Advanced Studies revealed harmonic layering, overlapping waveforms that modulated in perfect half-integer multiples, a behavior common in digital signal generation. At this point, the conversation shifted. What if 3i Atlas wasn't just constructed to survive interstellar travel? What if it was built to convey information through structure? Not a message in Morse, not a signal in sound, but a form-based encoding, where the shape itself carries data. Fractal encoding, after all, is one of the most efficient ways to compress and transmit complex information. It appears in biological systems, in synthetic data storage, and in some of the most advanced AI-driven image compression models. Could this object be doing the same, not just passively existing, but existing as an intentional geometry? One analyst wrote late that evening in a closed ESA forum, "We are not observing an object, we are observing a self-referencing container. Because when an object starts repeating its own design across scale, across spectrum, and across time, it stops behaving like a comet, and starts behaving like a code, one whose key might not be hidden inside it, but be the structure itself." As midnight crossed over the observatories in the Western Hemisphere on November 11, 2025, the global data stream on 3i Atlas began to resemble something strange, not just erratic, but cyclical. Observatories weren't just receiving confusing information, they were receiving the same information, again and again. At first, the repetition seemed like a glitch. The Atacama Large Millimeter Array in Chile noticed that a specific telemetry block, recording the object's microwave band emissions, looked identical to a set captured 6 hours earlier. Same amplitude, same interference spikes, same timing, down to the millisecond. But when compared to their raw instrument logs, the data wasn't duplicated on their end. The transmission had simply repeated, as if 3i Atlas had looped its output. This might have been dismissed as transmission lag or software caching, but then it happened again. At Greenbank Observatory in West Virginia, radio astronomers analyzing Doppler drift picked up an identical waveform from a prior scan. When they filtered out Earth-based interference and applied error-correcting codes, they found a 17 kilobyte chunk of radio data that had already been received 3 times that day. It was not a system failure. It was an external redundancy. This anomaly was confirmed by independent teams in Italy and South Korea, both working in different frequency domains. It didn't matter if the signal was light-based, radar, or thermal. The same structural loop, a block of data roughly 15 to 30 seconds in length, kept appearing in the recordings. Scientists began calling it the data loop. But the loop wasn't just in the emissions, it was in the object's behavior. Telescopic tracking logs from 12 different facilities showed that Atlas's rotational profile, the slight wobble detected in its outer envelope, also reset in a repeating pattern. Not just similar rotations, but identical attitude shifts and orientation snapshots every 41 minutes. It was as if the object had entered a holding pattern, or more disturbingly, as if it had never left one. Physicists at the Lawrence Livermore National Laboratory attempted to model the loop as a resonance effect, suggesting the object may have entered a natural feedback cycle with solar radiation or gravitational tides. But those forces don't explain data repetition. They affect motion, not information. So another theory emerged. What if Atlas wasn't sending new information at all? What if it was replaying a fixed sequence? That possibility took a darker turn when machine learning researchers in Berlin attempted to predict the next appearance of the loop using neural sequence modeling. The AI succeeded, almost too easily. It predicted not just the timing of the next loop, but the minute deviations within it, down to fractional power shifts. When it was asked to simulate 10 more loops in advance, it generated waveforms that were indistinguishable from the next live reception. This implied the loop wasn't random, and it wasn't reactive, it was encoded. More alarming still, within the loop, one of the embedded substructures matched a pulse cluster from a CT candidate signal detected in 2003, known as signal T46A. That signal was ultimately dismissed due to lack of recurrence, until now. So what does this mean? It means the data from 3i Atlas may not just be information, it may be a stored recording transmitted again and again. The object could be cycling through a fixed memory, as if delivering a time capsule or an instructional repeat. In computer science, this behavior resembles a boot loop, when a system reinitializes over and over without progressing. But in communications theory, it's closer to a beacon, a repeating signal meant to be noticed. Not dynamic, not responsive, just intentional. An ESA software engineer wrote in a closed memo that night, "We may be watching a cassette play itself on loop, embedded in an object moving through space." The question is no longer whether 3i Atlas is sending data. The question is, why repeat it, and for whom? At 02 Forstensen UTC on November 12, 2025, less than 24 hours after the initial signal loss event from 3i, Atlas, a lesser-known but critical problem emerged, this time in the realm of light polarization. The SO polarimetric array in South Africa had been quietly logging data across various filters, focusing on how incoming light from the object behaved when passed through polarization-sensitive optics. This technique allows researchers to decode the orientation of scattered light, revealing surface texture, field alignment, or atmospheric interference. But something was wrong. When the team applied their standard rotating polarizer analysis, the system flatlined. Across all angles, from linear to circular polarization, the system detected no modulation. It was as though the light from 3i Atlas had been scrubbed of its polarization entirely. This is highly unusual. Almost all reflected light, whether from ice, rock, or even dust, carries some measurable polarization due to the angle of incidence. But Atlas wasn't just low on polarization, it was in a state of complete lockout. In this state, no orientation of the polarizer filter changed the intensity of the signal. No interference fringe, no shift, just a perfectly neutral field, indifferent to every form of photonic filtering. This baffled the South African team, who initially assumed a calibration error. But within hours, the same result was independently confirmed by facilities in France, Chile, and the Canary Islands. Observations across 3 continents with different telescopes, filters, and instrumentation all returned the same result. 3i Atlas could not be polarized. This phenomenon was quickly labelled polarization lockout, and it had no known precedent in cometary science. Natural light, even from the most chaotic celestial objects, scatters in ways that leave behind partial polarization. Dust grains, mineral surfaces, and gas clouds all produce polarization signatures that can be studied and reverse modelled. Scientists use this to estimate surface texture, particle composition, and alignment of gas jets. But Atlas gave them nothing. The implications grew deeper when researchers at Max Planck Institute for Solar System Research applied a Stokes parameter analysis, a mathematical tool that breaks down the orientation and ellipticity of incoming light waves. The result was unsettling. A perfectly null vector field. In simpler terms, the light from Atlas was decohered, stripped of all directional bias, as if it had passed through a field scrambler that removed every trace of its origin or angle. This isn't just strange, it's anti-physical. Because polarization is not just a visual feature, it is fundamental to how photons behave. To erase it completely across multiple bands, radio, infrared, visible, suggests that either the light is being artificially filtered before it leaves the object, the light is not being reflected at all, it is being re-emitted, stripped of natural interaction with surface materials. Both options point away from natural processes. Further attempts to modulate the light using Faraday rotation, a technique that tests for magnetic influence on polarization, yielded no rotation at all. That meant not only was the light unpolarized, but it was also immune to magneto-optical effects. Even the James Webb Space Telescope, in a brief coordination test with ESA, failed to extract a measurable degree of polarization. Its near-infrared spectropolarimeter showed only a consistent flat band across all filters, a result described internally as uncannily sterile. So what would cause such a lockout? One speculative theory involves quantum decoherence, the breakdown of coherent states through interaction with an engineered medium. If 3i Atlas was surrounded by a field that destroyed wave alignment at the quantum level, it could theoretically erase polarization entirely. But doing that would require technology capable of modifying wave function behavior, not just for a few particles, but across entire wavefronts of light. This kind of control does not exist in any known natural or synthetic process, at least not on planetary scales. As one astrophysicist in Cambridge put it in a late-night call, this is not a comet, it's a veil, and it's choosing not to be seen. Because when light refuses to reveal direction, when photons arrive stripped of their past, and when every method of interaction fails, the message is no longer in the data. The message is the silence. By the early morning of November 12th, after nearly a full day of anomalies surrounding 3i Atlas, one signal stood out not for what it said, but for what it didn't. At exactly 3009 UTC, the Effelsberg Radio Observatory in Germany, was reviewing archival data from earlier in the day, searching for repeated structures in the narrowband emissions from Atlas. What they found wasn't a signal in the conventional sense, it was a pattern of pulses, sharp, measurable spikes in radio intensity lasting just fractions of a second, appearing in a non-rhythmic sequence. But it was what came between those pulses that drew immediate attention. The intervals weren't filled with static, noise, or cosmic background hum, the usual companions of deep space radio listening. Instead, they showed a total and unnatural silence. Not zero signal, not low-level noise, but perfect digital voids, as if the entire spectrum had been muted across all monitored frequencies. This wasn't expected. Natural objects, even quiet ones, always emit thermal background, especially in the microwave and infrared bands. Dust scatter, gas jets, or surface heating all generate passive signals. Silence in space is never absolute. There is always a flaw, a shimmer of entropy. But 3i Atlas produced none during those gaps. The phenomenon was quickly verified by Japan's Yasuda Deep Space Center, which had picked up the same emission pattern in K-band during a parallel sweep. Their instruments confirmed it. Between each burst of narrowband intensity, there were precisely 0 seconds of noise. Not even cosmic background radiation leaked through. And the silence was too clean to be accidental. The pulses themselves were odd enough, asymmetrical spikes that varied in amplitude and timing, inconsistent with any known rotating beacon or thermal oscillator. But the gaps, uniformly cold and signal dead, revealed a kind of intentional gating, as if a shutter was being opened and closed with unnatural precision. This led researchers to hypothesize the existence of a pulse-gate mechanism, a system capable of suppressing all emission across a wide band, not just from the object, but from the space around it. This could only occur under very specific conditions, possibly by manipulating the local vacuum field or damping radiation before it propagated. In engineering terms, it would be akin to placing a high-fidelity microphone in a recording studio and finding that even the air molecules refused to vibrate during certain moments. The signature was submitted to an international signal comparison system typically used by SETI. No match was found. But curiously, when the silent gaps were plotted across time, their distribution formed a non-random ratio, with clusters matching a Fibonacci-like spacing, known from self-organizing biological and mathematical systems. That was when researchers realized the pulses were likely not the message. The silence between them might be. It wouldn't be the first time science discovered meaning in absence. In quantum mechanics, zero-point energy is defined by what isn't there. In information theory, negative space is just as meaningful as presence. And in encryption systems, gaps and timing can encode more information than the signals themselves. When the silent intervals were mapped sonically and sped up to audible range, the sequence resembled a modulated rhythm, not quite music, not quite code. But it contained beat-like symmetry, too patterned to be ignored. A software engineer at the SETI Institute commented, "It's like listening to an orchestra where the instruments never play, only the rests between notes are performed, but the silence is so deliberate, it becomes its own language." If true, that would imply a negative language, one built from absence rather than presence, a vocabulary of voids. For a full 36 minutes, the pattern repeated across deep space monitors before abruptly stopping, replaced by the same chaotic reflectivity that had plagued Atlas all day. The silence was gone, but its footprint remained, because in the vastness of space, noise is expected, activity is assumed, but when something, or someone, suppresses every trace of interaction and lets only the void itself speak, that silence becomes the message. While much of the scientific world was still reeling from the pulse silence phenomenon, a smaller team working in Antarctica was quietly unlocking a very different piece of the 3i Atlas puzzle, one hidden not in light or signal, but in the object's structure itself. At Concordia Station, perched on the Antarctic plateau, researchers had been collecting long baseline interferometry data for over 18 hours. Their goal was to reconstruct high-contrast visual models of Atlas, using overlapping thermal and radar returns. The result, processed just after 4:20 UTC on November 12th, startled even the most seasoned observers. Beneath the bright outer shell of the object, beneath its icy facade and fluctuating coma, lay something darker, something that didn't move, didn't scatter, didn't reflect, and most crucially, didn't belong. The internal structure showed what researchers called subsurface shadows, sharply defined regions inside the object that absorbed all frequencies of active radar and rejected thermal mapping. Not cold zones, not dense rock, but signal voids, hollow shapes inside a solid comet. At first, the team suspected data corruption. Internal shadows of that sharpness typically indicate metal voids or foreign objects embedded within a matrix, something common in human-made alloys, but unheard of in naturally forming ice rock bodies. So they cross-referenced their data with the European Southern Observatory's VISTA telescope, which had taken deep infrared exposures earlier that day. The same shadows appeared, identical in position, depth, and angle, but this time in thermal negative. This meant the anomaly wasn't sensor-specific, it was real. One of the voids, shaped like a cylindrical cavity, ran almost the full length of the visible nucleus, measuring over 3 kilometers from end to end. It was surrounded by a region of glassy, reflective material that strongly resembled fused silica, a substance that only forms under intense heat or pressure. Another shadow, deeper in the core, resembled a nested spiral, a repeating structure that twisted inward, vanishing into the object's center. This internal formation had no analogue in cometary science. It absorbed light in all bands, yet appeared to retain perfect geometric symmetry, like a chamber carved by design rather than formed by chance. Researchers began modelling the object as hollow core with embedded geometry, something no comet had ever exhibited. Most small interstellar bodies are chaotic, a jumble of dust, rock, and volatile gas. They break apart, tumble, and outgas. But Atlas was intact, symmetrical, and apparently partitioned on the inside. This changed everything. If these shadows were cavities, what were they for? If they were chambers, what did they hold? Some speculated cryogenic storage. Others suggested gravitational dampers. But one theory began gaining quiet traction across encrypted scientific chat groups. The shadows were not structural. They were optical null zones, places designed to hide information. In stealth technology, radar-absorbing cavities are used to deflect or scatter incoming waves. In optics, hollow resonators trap light and can delay or manipulate its release. If such technologies were scaled to kilometer-sized architecture and embedded inside a moving body, the result would be something like Atlas, a ship that looked like a rock, but acted like a mask. The final confirmation came from an unexpected source, the Indian Space Research Organisation, which had recently launched a polar observation satellite capable of synthetic aperture radar mapping. When pointed at Atlas, it registered 3 distinct absorption pits, perfectly aligned, equidistant, and forming a straight line not along the object's rotational axis, but along the Sun-Earth vector. Someone had built these cavities on purpose, aligned to something, or someone, watching. The team at Concordia Station issued a single-line summary in their post-analysis file. These are not shadows cast by light. These are shadows cast by intent. For the first time in modern astronomy, scientists weren't just speculating about what an object was made of. They were asking why it contained things it didn't want us to see. By mid-morning on November 12, 2025, one of the most trusted methods for studying space, Doppler shift analysis, began to fail under the pressure of 3i Atlas. What had started as a stable tracking operation using velocity-based spectral data became a confusing tangle of contradictions. The object was no longer moving in a way that could be measured with certainty. It was, in essence, moving in 2 directions at once. This wasn't a metaphor. It was an observational fact. Doppler measurements are the backbone of modern astrophysics. When an object moves toward a sensor, its light or radio signal compresses, shifting to a higher frequency, or bluer tone. When it moves away, the signal stretches, lowering its frequency or becoming redder. This principle is used to measure orbital speed, distance, and trajectory with great precision. So when 2 major facilities, the Goldstone Deep Space Network in California and the Nancy Radio Observatory in France, reported opposing Doppler shifts from the same object, at the same time, it triggered an international data review. Goldstone's high-gain antenna showed a clear redshift, consistent with 3i Atlas receding along its expected escape path past Earth. But Nansei's wide-angle dish, which had been running a redundant sweep at a slightly lower band, showed a blue shift, as if the object were approaching. Both results were time-stamped within 3 seconds of each other. Both were based on clean, filtered signals. Both were correct, according to their own data environments. This contradiction became known within hours as the double Doppler conflict. Initially, analysts believed it to be a relativistic echo, a known artifact where strong gravitational fields or plasma lensing can bend a signal path, making it appear to shift in frequency. But Atlas was not near any large gravitational source, and there was no coronal mass ejection or solar flare to create such effects. In fact, the heliosphere was unusually calm that day. So the question became, how could one object emit a signal that simultaneously showed it receding and approaching? The answer, or at least the hypothesis, came from a team at the University of Tokyo, working on a modelling technique called Doppler vector folding. By reconstructing the trajectory and spin of Atlas, they proposed that the object might be emitting along 2 different frequency corridors, each modulated to appear shifted relative to a different observer's position. In short, 3i Atlas wasn't just reflecting light. It was emitting custom Doppler signatures, perhaps even deliberately. One possible explanation: the object contains a rotating frequency engine, a system that beams directional signals with slight time offsets, creating the illusion of multi-directional motion. This would be similar to how radar jamming aircraft confuse incoming tracking systems by splitting their signal signature across several bands. But there was a deeper implication. When a third observatory, Parkes in Australia, joined the analysis and found both redshift and blueshift components present within the same spectrum, it became clear the signals weren't just a matter of perspective. They were coexisting, encoded within the same emission, defying standard motion logic. This led to a terrifying conclusion. 3i Atlas might be non-inertial, not bound by a single trajectory, but oscillating across vector frames like a phased object. If true, it would mean we are watching an entity move through space in ways we cannot yet describe. As one astrophysicist wrote in a locked internal NASA forum, if these signals are accurate, then Atlas is the first object we've recorded that violates classical Doppler symmetry. It's not just moving, it's presenting motion. And it might not be moving at all, just playing back the illusion. A second researcher added, we measure with waves, but what if it bends those waves before they reach us? For centuries, the Doppler shift has been a reliable truth, a way to glimpse the behaviour of things we cannot touch. But now, something was using that trust against us, not breaking the law of physics, but bending it, ever so slightly. And if Atlas could do that with light and velocity, what else could it alter? By the late afternoon of November 12, 2025, the global network of observatories tracking 3i Atlas was facing a new kind of breakdown, not in equipment, not in power, but in consensus. For nearly 2 full days, the world's finest instruments, from deep space antennas to infrared satellites, had all agreed on one thing. 3i Atlas was an enigma, but at least they were all observing the same enigma. That changed with the emergence of what researchers began calling sensor harmonization drift. It began quietly. The Mauna Kea Infrared Telescope in Hawaii noticed that their baseline temperature readings of Atlas had begun to diverge from the expected blackbody curve. While the nucleus had consistently emitted at a cold, stable 190 degrees Celsius, new frames showed a rise of almost 4 degrees over just one orbit sweep. That wouldn't be strange on its own, if not for the fact that every other telescope still measured the original temperature, including instruments with nearly identical resolution and calibration. This wasn't a shift in the object, it was a shift in perception, specific to individual sensors. Within hours, NASA's SOFIA Flying Observatory recorded a similar misalignment in spectral band overlap. The water vapor emission lines previously noted in Atlas's coma began to broaden, not because of internal activity, but because their spectrometer began drifting out of sync with itself, frame to frame, in real time. The instruments weren't broken. They were being nudged off calibration, one fraction at a time. As observatories compared notes, the anomalies multiplied. The James Clerk Maxwell Telescope in Hawaii and the IRAM 30-meter dish in Spain ran simultaneous scans at 230 GS. In theory, their results should have matched, but they didn't. The Spanish team saw a sharply defined central emission with minor phase drift. The Hawaiian team reported a fragmented spectral line, almost as if the object had split into two weak sources. Each group recalibrated, rechecked logs, rebooted, same result. The issue wasn't hardware, it was harmonization, the ability for two instruments to agree on what they were observing. That ability was failing. Across the globe, datasets that should have aligned within margin of error were now drifting apart. Slight frequency shifts, minor Doppler mismatches, curvature errors, thermal scatter that existed in one reading but not another. It was as if 3i Atlas was becoming observer relative. And then came the truly chilling realization. When teams attempted to overlay their sensor data to create a composite image of the object, the kind typically used to increase resolution, the result was not clarity. It was interference. The composite images became blurred, inverted. Some even appeared symmetrical, as though the data from multiple sensors was cancelling itself out, creating false negatives where there should have been structure. This was not a technological problem. This was a perceptual destabilization. The term sensor harmonization drift became formalized in a joint ESA-NASA memo that day, defined as the progressive and unpredictable divergence of synchronized instruments when observing a shared astronomical target, resulting in non-overlapping, non-integratable datasets despite identical observational parameters. In simple terms, instruments no longer agreed on what reality looked like. Some theorized the object might be emitting phase-tuned signals designed to shift slightly depending on the sensor orientation, causing minor harmonic dissonance. Others proposed a localized quantum decoherence effect, where observational particles themselves experience spatial uncertainty when interacting with Atlas's field. But a more philosophical idea took hold late that night. What if 3i Atlas wasn't evading detection? What if it was fragmenting reality? Just enough to keep every eye confused in a slightly different way? A comet can hide behind dust, a machine can hide behind silence, but only something truly advanced could hide by making every observer disagree on what is even there. It was no longer just a matter of what 3i Atlas was, it was a matter of how long we could keep looking before our instruments, and our models, fell out of sync entirely. At 1903 UTC on November 12, 2025, the object known as 3i Atlas did something that no comet, no spacecraft, no astronomical body has ever done in the era of continuous observation. It blinked, not vanished, not exploded, not outgassed. It simply disappeared and returned across every global tracking system in perfect synchronization for exactly one frame of observational time. The first to catch it was the Canada-France-Hawaii telescope, running a high-speed photometric sweep. Their system captured a frame-by-frame series of the object's nucleus, measuring minor fluctuations in albedo. Between time-stamped frames at 1902 59.12 and 1903 0114, 3i Atlas was gone. Not dimmed, not obscured, gone, no brightness, no movement trail, no dust echo. Just raw background stars perfectly exposed as if nothing had ever been in the frame at all. And then, in the very next frame, it was back, in the same position, same vector, same apparent spin. 2 seconds, one gap. They assumed a software fault. But minutes later, Lick Observatory in California, the Royal Astronomical Society in London, the Gaia probe, and even China's FAST telescope all reported the same thing. A momentary global absence, with zero telemetry across all frequency domains. It was as if someone had blinked reality itself. The incident was named simply the blink. This wasn't an occlusion. It wasn't a solar flare. It wasn't a data buffer overflow or cloud interference. These systems were redundant, triple-checked, running at different latitudes and altitudes. Many weren't even in Earth's atmosphere, and yet all of them saw nothing at the exact same moment. The closest physical analogue would be a quantum tunneling event, where a particle briefly moves between two positions without existing in the space in between. But Atlas isn't a particle. It's several kilometers wide, emitting thermal, optical and radio signatures. To not exist for 2 seconds would require a suspension of every known physical constant. And yet, that's what was recorded. Some theorists posited a micro-dimensional phase shift, a brief moment where Atlas ceased to interact with our observable universe, like a frame dropped from a film reel. Others believed it was a local manipulation of time, not time travel, but a localized pause, affecting only the object while the rest of the universe moved forward. But then came the deeper horror. When some facilities, including the Very Long Baseline Array, replayed their raw observational logs, that missing frame wasn't corrupted or blank. It was simply missing from the record entirely. Even their logs had blinked. This suggested the event wasn't just optical, it was informational, as if the object had reached into the flow of recorded data and edited itself out, retroactively. No memory, no cache, no time-stamped remnants. One observatory in Spain found its automated tracking software had paused for exactly 2 seconds. It hadn't crashed. It hadn't thrown errors. It had simply not run. There was no gap, just a seamless skip like a black frame in a movie reel. The program resumed without any awareness it had been blind, and still, the object reappeared with the same momentum, the same orientation, the same radiation profile. No loss of energy, no trail, no consequence. It was as if nothing had happened, except everything had. Theories poured in, a stealth system beyond human comprehension, a navigation technique based on reality modulation, a defense mechanism triggered by synchronized observation. But the most haunting possibility wasn't technological, it was intentionality. Because only something aware it was being watched would time its disappearance so precisely. Only something with total environmental awareness would reappear in perfect continuity. And only something that understood our systems, our sensors, our physics, our assumptions, would know that 2 seconds of nothing could be louder than 2 hours of signal. After the blink, all instruments remained operational, but no one could explain what had happened, because when something that large can decide not to be seen, even for just 2 seconds, it changes the nature of the question we're asking. The mystery is no longer what is 3i Atlas, it's who or what is watching us back.